Hello everyone. Welcome to the sixth lecture of Module 4 in Verilog HDL. So, in this part, we are going to study about tasks and functions. So, this is the second part of Module 4. The first part of Module 4 and the previous lectures till now, we have studied about the concepts of behavioral modeling. So, in this lecture, let's continue with the concepts of tasks and functions. So these are the learning objectives of this lecture. Describe the differences between tasks and functions. Identify the conditions required for tasks to be defined. Understand task declaration and invocation. Explain the conditions necessary for functions to be defined. Understand function declaration and invocation. So, first of all, let us know the differences between tasks and functions. First difference is a function can enable another function but not another task, whereas task can enable other tasks and functions too. Second difference is functions always execute in zero simulation time, whereas tasks may execute in non-zero simulation time. Functions must not contain any delay, event, or timing control statements, whereas tasks may contain delay, event, or timing control statements. Functions must have at least one input argument. They can have more than one input also, whereas tasks may have zero or more arguments of type input, output, or inout. And functions always return a single value and they cannot have output or inout arguments, whereas tasks do not return with a value but pass multiple values through output and inout arguments. These are the differences in between tasks and functions. With this basics, let's continue to know in detail about the tasks and functions. So, starting with tasks. Tasks are declared with the keyword task and they end with the keyword end task. And tasks must be used if any one of the following conditions is true for the procedures. So, the first condition is if there are delay, timing, or event control constructs in the procedure. So that tasks must be used. Second condition is the procedure has zero or more than one output arguments. In that case also tasks must be used. Third condition is the procedure has no input arguments. In that case also tasks can be used. Moving further, let's know about the task declaration and invocation syntax. So first of all, how is the task declaration syntax? Task is always declared with the keyword task followed by the name of the task, ends with a semicolon. In the initial part of the task, we can do the declaration and followed by the program statements, and the task ends with the keyword end task. So the invocation syntax for task is as follows. So the task can be invoked beginning with the name of the task. So we can invoke a task by the name of the task followed by the input and output arguments that are to be passed. So in the task invocation statement, where it begins with the name of the task followed by the input and output arguments, the input and output declarations use the keyword input, output, or in-out based on the type of arguments declared. So in a task, the input and output declarations can use these keywords. Input and in-out arguments are passed into the task. Means when we pass in an invocation statement, the input and in-out arguments are passed on to the actual task. So then the input arguments are processed in the task statement. So once the input arguments are passed, so they are processed in the task statement. Output and in-out argument values are passed back to the variables in the task invocation statement when the task is complete. Means after passing the input arguments, so which are processed, and the results or the values are passed back to the variables in the task invocation statement. And tasks can invoke other tasks or functions. Now, let's see an example of task declaration and invocation. We have chosen an example here to define a module called operation, which contains the task by name bitwise underscore OPER. Module begins with the keyword module followed by the name of the module operation. So here we have declared a parameter by name delay, which is equal to 10. A and B are of 16-bit registers, and AB underscore and AB underscore OR and AB underscore XOR are 16-bit registers. So which are the outputs? A and B are the inputs. So always at followed by the sensitivity list. So that is which includes the inputs A or B. Whenever there is a change in the inputs, then the statements within always will be executed. So beginning for the always with the keyword begin. So this is the task invocation statement, which begins with the name of the task. Bitwise underscore OPER is the name of the task, followed by the outputs. AB underscore and AB underscore or AB underscore XOR are the outputs, and A and B are the inputs. So module ends with the keyword end and end module. So here we have the task bitwise underscore operator declared, which begins with the keyword task followed by the name of the task. So whenever the program simulation comes to this statement, so it will search for a task by the name bitwise underscore operator here. So here in this task, we have declared AB underscore and AB underscore or AB underscore XOR as 16-bit outputs. A and B are 16-bit inputs. So here the input values, that is A and B, are passed on to the inputs A and B here, which are further processed, and the results or the outputs are passed on to the output variables in the task invocation statement. So here we are going to pass multiple values from the task to the task invocation statement. So task ends with the keyword end followed by end task. And module ends with the keyword end module. Further, let us see one more example of asymmetric sequence generator by using tasks. So here, this example directly operates on a register variable clock to continuously process the asymmetric sequence. So here the clock is initialized within an initialization sequence, and further it is asymmetric sequence is generated. Here the module begins with the keyword module followed by the name of the module, that is sequence. Clock is declared as a register, initialization sequence. Let us see how this task by name init underscore sequence is written to generate the asymmetric clock generator. So begin asymmetric sequence. So here we have written a task for initialization sequence to initialize the clock. So task begins with the keyword begin, where we have initialized clock is equal to 1-bit binary 0, and the task ends with the keyword end task. And here this is the task asymmetric underscore sequence. Keyword task followed by the name of the task. So beginning of the task. So here we have several statements with different delays defined, where the clock will remain in that particular state for that duration of time. So here in this statement, #12 clock is equal to 1-bit binary 0. Clock will remain in 0 state for 12 time units. The next statement, clock will remain in 1 state, logic 1 state for 5 time units, followed by clock in 0 state for 3 time units. And the last statement, clock remains in logic 1 state for 10 time units. So in this way, asymmetric clock sequence will be generated here. So the task ends with the keyword end and end task. So this is how we can write a task for asymmetric clock generator. Further, let's know about automatic or reentrant tasks. So if a task is called concurrently from two places in the code, then these tasks will operate on the same task variables so that the results will be incorrect. So when we pass two different variables from two different places, then obviously the results will be incorrect. So to avoid this problem, what we can do is we can declare an automatic task where a keyword automatic is added in front of the task to make it reentrant. So such tasks will be called as automatic tasks. So what happens in an automatic task? How will it help to overcome this problem? So all items declared inside automatic tasks are allocated dynamically independent memory for each invocation. And hence, each task call operates in an independent space and hence results in correct operation or correct results. Now let us see an example for reentrant tasks. So here we have chosen a module by name top. Here we have CD underscore XOR and EF underscore XOR as 16-bit registers. CD, EF are also 16-bit registers. So these are inputs and these are outputs. We have declared an automatic task here where the keyword task is followed by the keyword automatic followed by the name of the task. Bitwise underscore XOR is the name of the task here, followed by the input and output declarations. Begin. Here we have written a statement for AB underscore XOR is equal to A XOR B. So the XOR of A and B will be computed and assigned to AB underscore XOR here. Task ends with end and the keyword end task. So here we can observe that. So we have two concurrent calls for the task bitwise underscore XOR from two different modules here. So always set POSIX of clock. So bitwise underscore XOR, the output argument here is EF underscore XOR with the inputs E and F. So here the inputs are C and D. So when two concurrent task calls are made to pass the values EF and CD to AB, so now what happens? So since the task is declared as automatic, then two independent spaces will be allocated to these two independent task calls and hence proper results will be computed and the results will be stored in independent memory locations and hence the results will be correct. So this is how automatic tasks will help to overcome incorrect results when several concurrent calls are made to a single task. Let's move further with functions. Functions are declared with the keywords function and they end with the keyword end function. Functions are used if all of the following conditions are true for a procedure. So, what are the conditions here? So, they are, first one is, there are no delay, timing or event control constructs in the procedure. Second one is, the procedure returns a single value. So this is very important here. The procedure must return a single value. There is at least one input arguments. So there cannot be zero input arguments, but at least there must be one input argument. Now let us know about the function declaration and invocation syntax. So the function declaration syntax is as follows. Function declaration begins with the keyword function followed by the range or type, so which is optional, followed by the name of the function, ended with a semicolon. Initial part of the function will have the declaration part followed by the program statements, and function ends with the keyword end function. So here in the function declaration syntax, range or type can be, will be the range of the data what we are going to use in the function, and the type can be integer, real, like that. So in the function declaration part, what all can be declared? So we can declare parameters, inputs, registers, time, integer, and real. And the name of the function is a identifier, so which is a user-defined name. Now let's see the invocation of a function. So how is the function invocation syntax? A function is always invoked beginning with the name of the function followed by the expressions. So here in a function invocation call, so there are no output arguments. So in this invocation call, there will not be any input output arguments. So for functions, because the implicit register name of the function means once we declare the name of the function, so that will be implicitly declared as a register which will contain the output value of the function. Functions cannot invoke other functions. So, whereas tasks can invoke functions, whereas functions cannot invoke other tasks, and they can only invoke other functions. So now let's continue with an example of how to invoke and how to declare a function. The first example here models a parity calculator that returns a 1-bit value. Let's see the example. So here, the function that calculates the parity of 32-bit address and returns the value. So here we have the example of declaration and invocation of the function. The module begins with the keyword module followed by the name of the module, that is parity. Here address is declared as a 32-bit register and parity is 1-bit declared as 1-bit register, always at followed by the sensitivity list. So whenever the parameter in the sensitivity list changes, the statements within always will be executed. So begin for always. So parity. So this is the function invocation statement. Parity equal to, so this is the function name, calculate underscore parity, followed by the input arguments. So here, once the name is declared, so implicitly a register will be declared in the name of the function. So next we have a statement to display the value of the address. So that is $display is the system directive used to display the parity calculated. So here module ends with the keyword end. Here we have written a function which begins with the keyword function followed by the name of the function, that is calculate underscore parity is the name of the function. Here address is a 32-bit input. So in the function invocation call, so we pass the input arguments. So here the input arguments are received and processed here, and the result which is assigned to the name of the function itself, calculate underscore parity, is itself the name of the function which will be assigned with the result, and it will return back to the function call. So in this way, we'll not have any explicit output arguments in a function. So it ends with the keyword end followed by end function. End function is the keyword to end the function. So this is how we can declare and invocate a function in Verilog. Moving further here. So here, the first invocation of the calculate underscore parity here, the returned value was used to set the register, that is parity. And the second invocation here, the value returned was directly used inside the $display task. Thus, the returned value is placed wherever the function is invoked. Means once the values are processed, so the returned value is placed exactly where the function will be invoked here. So this is how the computed value will be returned back to the function where it is invoked. So let's continue with automatic or recursive functions. So we have come to know about automatic or recursive tasks also. So the concepts are exactly similar for a function also. So here, if a function is called concurrently from two places in the code, then these will operate on the same variables and hence the results will be incorrect. So to avoid this problem, a keyword automatic is added in front of the function to make it reiterant. So then such a function will be called as an automatic function. So in each call to automatic function operates in an independent variable space. So whenever there are concurrent function calls, then made to an automatic function, so they'll operate in an independent variable space. Automatic function references cannot be accessed by hierarchical references. So this is very important here. So automatic function references cannot be accessed by hierarchical references. And hence each function call operates in an independent space and hence results will be correct. So where the results will be incorrect if the function calls are not, if the functions are not declared to be automatic, and simultaneously if we have concurrent calls to a function. So let's see an example now. So here we have an example for calculating the factorial of a number. Here we have defined a module by name top. Here we are going to declare the function which begins with the keyword function followed by automatic. So keyword automatic which declares the function as of automatic type, followed by the type. So integer is the type, followed by the name of the function, that is fact. So function, keyword function, followed by the keyword automatic to make the function automatic. So followed by the type, followed by the type, and which is followed by the name of the function. Here we have declared OPER as a 32-bit input. I is a variable of type integer. Beginning of the function with the keyword begin. If OPER is greater than 2, if the input value is greater than 2, then we have written a function here to compute the factorial of a number. So as we all know the procedure of calculating the factorial of a number. So here fact is equal to factorial of operand minus 1 into operand. So if the value of the input number is greater than 2, then we go on taking the successive products to compute the factorial of a number. So else, if the number is not greater than 2, then factorial is equal to declared as equal to 1 here. End is the keyword used to end the function. That is, with the keyword end function, the function will be ended here. So when we are going to call a function, so let's see what happens. So in a function call here, so here we have declared res result as of type integer, initial begin. We have the statement for function invocation here. So res is equal to fact of 4. So here fact is the name of the function followed by the input argument which is to be passed. So we want to calculate the factorial of number 4. Then this value of 4 will be passed on to the input argument here. So OPR will receive the value 4, factorial will be computed, and the result, what is assigned to fact here, will be moved back to the function invocation call. And we also have written a display statement here to display the result. So where the result will be displayed as 24. So here the function module ends with the keyword end and end module. So in this way, when there are concurrent function calls made to a single function by declaring the function as of type automatic, so we can avoid the errors in the results. So since concurrent calls will operate in independent memory locations. So this is the summary of the topics what we have discussed in this lecture. So let's go through the summary. Here in this lecture, we have studied about tasks and functions, which will help to make a module definition more readable, and it will help to divide them up into manageable subunits. In spite of writing a bigger continuous program, so we can divide them into manageable subunits. Tasks and functions serve the same purpose in Verilog as subroutines do in C. So as we write subroutines in C, so tasks and functions are similar to that in Verilog. Tasks can take any number of input, in-out or output arguments, and delay, event or timing control constructs are permitted in tasks, and tasks can enable other tasks and functions too. Whereas functions are used when exactly one return value is required. If more than one return value is required, we cannot use a function. So, and at least one input argument must be specified in a function. Delay, event, or timing control constructs are not permitted in functions, whereas they are permitted in tasks. Functions can invoke other functions, but cannot invoke other tasks. A register with name as the function name is declared implicitly when the function is declared, and hence we do not require output arguments in a function. The return value of the function is passed back to this register, that is the name of the function itself. Tasks and functions are included in design hierarchy and can be addressed by hierarchical name referencing. So this was about the concepts what we discussed in this lecture. So further, let us go through few MCQs to know whether you have understood the topics properly or not. So first question, function has input, output and in-out port as argument, have one input argument only, can have more than one input arguments, can have both input and output arguments. So which is the correct answer here? So can have both input and output arguments. So here for this question, option D is the right answer. So second question, task and function cannot have, first one, registers, time variables, local variables, option D, wires. So tasks and functions cannot have registers. So coming to the next question, which is true about task and function? First question, first option is task and function contain always and initial blocks. Second option, task and function do not contain always and initial blocks and called from initial and always blocks or other tasks or functions. Third option, task and function do not contain behavioral statement, and option D, none. So option B is the right answer here. Task and function do not contain always and initial blocks and are called from initial and always blocks or other tasks or functions. Fourth question, functions execute in zero simulation time. Option A, true, and option B, false. So functions can execute in zero simulation time and hence option A is the right answer. Next question, tasks may contain delay, event or timing control statements. Option A, true, and option B, false. So task may not contain delay, event or timing control statements. So actually tasks can contain delay, event or timing control statements and hence the statement is false. So option B is the right answer. Sixth question. So there are no output arguments for functions. Option A, true. Option B, false. So option A is the right answer here. So next question. Automatic function references cannot be accessed by hierarchical references. So option A, true. Option B, false. So automatic function references cannot be accessed by hierarchical references. So option A, true, is the correct answer. So we have discussed about tasks and functions in this lecture. So hope you have understood the topics well. Let's meet in the next lecture. Thank you for patient hearing. So this is our team and these are the references which we have referred to prepare this presentation. Thank you.